All right, so hello and welcome. So this is going to be some more SU2 applications. So we looked at the isotropic harmonic oscillator in the previous lecture, and today what we're going to do, we're going to look at the Bohr atom. Now, Bohr's hydrogen atom is very, if you wish, uh, a very important uh, uh, very important thing in quantum mechanics. So this is described by Hamiltonian of a particle of momentum p, charge e, and mass m, which is bound by an attractive Coulomb potential. So here you have the Hamiltonian. Hope this is visible. The um, scan does not look very good, but just so that you can understand what is going on. That's an H. Is equal to P dot P vectors pi twice M minus E squared over R, where R is given by the square root of the dot product of these X vectors. Okay, so that. And the spectrum of negative energy bound states should be familiar to you, and this is given by this En is equal to minus some R of Y. R of Y is called the Rydberg's constant by n squared. As you remember, the levels are it's given by 1 over n squared, where n is the principal quantum number, which ranges from 0. It ranges from 1 to so on and so forth. And you should also remember that each of these levels is polluted by is not polluted, populated by states of angular momentum L is equal to 0, 1, 2, up to n minus 1. Okay. Now, it's very clear that the Bohr atom is manifestly rotation invariant. Therefore, what is going to happen is that the angular momentum operators that we also came across last time around, these are going to commute with the Hamiltonian. So this is what we have by this. Okay. And what we did is in the previous example is that very similar to that. It just means that this invariance is just going to mean that the levels of the same energy will now come in sets of representations of this rotation algebra. So SO3 or SU2 if you wish. It is the case, but interestingly, what happens is that the first excited level is not made up of one, but two separate SO3, SO3 representations. The one which has L equal to 1 and the other which has L equal to 0. Okay, so that's the fun. And okay, so this implies that actually there is more symmetry here than meets the eye. And in particular, this hints at the existence of some some operators, uh, three operators. Actually, that is going to map L equal to 1 to the into the L equal to 0 state. So we will infer the existence of such an operator, which uh, we infer that there is the existence of such an operator, which commutes with the Hamiltonian and is a vector under these SO3 operations. Okay. This again is something that has been known for quite a while, and it's known in the uh, context of the Keplerian problem in uh, classical mechanics, which uses the same form of the 1 over r squared potential that we had. 1 over r uh, thing that we had earlier, and this is just classically just this uh, pi. Sorry, let's get this right. P cross L minus this me squared x by r. So this is, I mean, the vectorial form of this is here. So that's the usual classical form. Now, what we do is we want to understand this in the quantum sense. Okay, so if you want to understand this in the quantum mechanical sense, what we will do is we will symmetrize the momenta and the angular momenta to get its Hermitian form. And if you do that, so what we are going to do is we are going to write this PILK in a form that is symmetric. This we want this to be Hermitian, as I said. So PILK plus LK, PJLK plus LK PJ. And remember that if you want to take one through the other, this is going to give you a non-zero, non-zero uh, answer at the end of the day. So so that is what you end up with, and what you'll see is that you'll find here that you get this extra IPI piece. Okay. All right. So what you can check is that these if you dot the L's with the A's, you'll see that this is equal to 0. So A is actually, as a vector, this A is actually orthogonal to the L's that we had earlier. So you can check this, and this should be again straightforward. And it's also it's something that you can again sit down and do. Just use this form of the AIs, and again it should be pretty obvious to you that what I mean, you can actually sit down and do this. You will find that Li with Aj is I epsilon Aj Lk. Now, again, the next line is an analysis that I would urge you to do with all of these. With all of these, you can now work out what the Hamiltonian or what the bracket of the Hamiltonian with the AI is, and this again turns out to be 0. So it just means that this vector is a constant of motion, and that the Bohr the Bohr Hamiltonian is actually invariant under under the transformations that this generates. This is not manifest at all, and this is something which is called a hidden hidden symmetry. You'd be familiar with some of this from your from what you had done earlier in classical mechanics, but that's the upshot of this. And what we can use this for is that it'll give you a quick and elegant solution to the Bohr atom. And so what you do is you start off by I mean computing the commutator of AI with Aj, and that is a result which is in a simple form like this. So this gives you epsilon ijk lk, and it also gives you minus twice mh. So as I said earlier, the Bohr atom, is going to describe a bound system. So the, energy eigenvalues will have a sign to. So in that case, what you get out here is not a problem, and so we can define something called AI hat, whereby we also are going to divide it throughout by minus twice mh. And remember that since h is going to commute with both L and A, this is not going to be a problem, we will not have, I mean, I mean, issues with, uh, a non-trivial A with H or A with, I mean, L with H. So in this redefined way of trying to look at the A's, so these A hats now satisfy the much simpler, I mean, sort of relation here with AI hat and AJ hat being equal to I epsilon IJK LK. And we close the algebra as well. So now what we note is that if we look at these linear combinations, we call these x plus and x minus, which will be Li plus minus Ai. So these are going to, I mean, when you look at x plus with x minus, that gives you a 0. But x plus and x minus independently also generate an SU, I mean, SU2 Lie algebras, right? So these form two independent SU2 Lie algebras. And the invariance algebra of the Bohr atom thus becomes a direct product of these two SU2s. Okay. The Yeah, I mean, the quadratic, quadratic Casimirs of these two algebras are should also become equations of motion. But what we can see from here is that this C2 is given by this C2 plus, if you wish, goes by this, and C2 minus goes by this. But also remember that L dotted with A is equal to 0. So the cross terms. So let me just make sure that you understand that this is a plus. Let me highlight this. So this is a plus, this is Li, and these are also Li's, but that's a minus. Okay. So but remember that this is L dot A is equal to 0. So this essentially amounts to C2 plus being equal to C2, I mean, C2 minus. Okay. So that essentially also means that C2 can, with in the usual, I mean, SU2 way, it can be written as J1 into J1 plus 1, and C2 minus is written as J2 into J2 plus 1. So this would mean that J1 is equal to J2 equal to J. Okay. So now what we will do is we will express the Hamiltonian in terms of these quadratic, I mean, the Casimir operators, and we will do this by looking at the length of the what's it again? The Runge lens vector. Laplace Runge lens vector. So that's the extra L. I'm sorry, got lost there for a minute. So yes, so now this is a little tricky, but what you can do is you can. So this is going to be something that I'm going to leave as an exercise for you guys. So you can look at the, look at the evaluation of this, and AI ultimately turns out to be something which is, uh, given by the right hand side here. Okay. Um, all right. So that's one thing. And once you have AI, you can divide both sides by twice minus twice HM, and you can get the Hamiltonian in the form of the things that we had written earlier. So the relation between the Hamiltonian and the uh, I mean and the C2 is explicit, and in terms of J, this is just given by this last expression out here. So this shows that J is not the angular momentum, but is actually related to the principal quantum number n, then and that is n is 2j plus 1. Okay. The sum, the I mean angular momentum actually is the sum of the two independently algebras. So Li is given by xi plus xi, xi minus. What we can do is we can try and find the degeneracy of these uh, levels with n equal to 2j plus 1. This essentially amounts to listing the states in the sort of direct product of 2j plus 1 and two of these guys. So this is the classical problem of angular momentum. Now the same j, and it's yield states with yield states with angular momentum L is equal to 2j, and then 2j minus 1 and so on and so forth. So this is n minus 1, this is n minus 2 and so on and so forth. Again, this is a well known answer. All right. So yeah, so the last thing that I wanted to mention here is the all of this was first done by Pauli, who derived the spectrum of the Bohr atom by recognizing its symmetries and using this power of the SU2. So these were two applications. You saw one in the last class, and we have gone through one a little quickly, I would say, in this class. There are other applications as well. For example, there's something called isospin. What is this? This is the fact that protons and neutrons are approximately the same in terms of mass, so they can be thought in as a sort of doublet of a new SU2, and this is called isospin. And you can use this to I mean figure out what is happening in so you can use this to try and figure out, say, the uh, nucleus and so on. That is But you also have to keep in mind that this is not exactly true. So if you when you are going to be looking at this in more detail, you have to understand that by as a symmetry, which is actually which will be broken um, when you look at, for example, the weak forces and electromagnetic forces. If you look at them at the same time, it will actually appear that they're not the same. Okay, so of course, the reason being that the protons are charged and the neutrons are not. Um, so if you wish, this isospin invariance only applies to nuclear forces, and it will not be there when you look at electroweak things. Yeah, so that's there. That's one more application of the SU2, and there are of course we need to also since we are saying things about SU2, this is one has to actually also mention that one of the major uses of SU2 in physics is using it as a gauge group. And just like, as you might have learned, or you will learn in some time, electromagnetism can be understood as a gauge theory of where the underlying gauge group is U1. You can think about the theory of weak interactions being modeled as an SU2 gauge group, and this is something that explains the modern theory of things like the beta decay. But we will not have much to say about this part, unfortunately. This is beyond the scope of what we want to actually discuss here. So that was that in the sense that you have now had a pretty substantial look at SU2s, and and uh, how to build its representations, and different aspects of it, how it's related to how it's related to the group SO3, and the fact that it's the same on the algebra level, but at the group level it's not the same. And now you've also have some selected applications which we have had a look at. Now that we are done with the SU2s, we will see that what we have learned here will be very useful going forward and try to understand the other groups. And we will try to use this, okay? So the next lectures will be trying to build on this and trying to build on what we have learned in the case of SU2s and try to take that to, higher groups, okay? So that's it for now, and I shall be uploading something else very soon. So thank you.